Hello, I'm Tom Buckholtz. Welcome to this presentation, New Thoughts, Suggestions, and Results about the mysterious world of elementary particles, dark matter, and dark energy. Let's preview some of the mysteries for which I offer solutions, or at least pointers to possible solutions. People use a chart such as this one to depict all known elementary particles. Since the year 1995, people have found only one new elementary particle, the Higgs boson. People tend to believe that nature includes other elementary particles. What are the other elementary particles? How might people detect or infer the other elementary particles? People tend to believe that for each one of many galaxies and many larger objects, such as galaxy clusters, more than 5/6 of the stuff is not ordinary matter. The invisible stuff might be dark matter, but what is dark matter? People observe that, on average, large structures, such as galaxy clusters, generally move away from each other. People tend to say that dark energy phenomena govern changes in the rate at which objects separate from each other. But what is dark energy? People speculate about relationships between physics constants, such as the speed of light, properties of objects, such as the mass of the electron, and relationships between constants and properties. To what extent are seemingly unrelated quantities actually meaningfully interrelated? Results that I present include predictions for new elementary particles, explanations for effects and data that people associate with the term dark matter, explanations regarding eras in the evolution of the universe, and links between physics constants, properties of objects, and aspects of fields. People have pursued each of the four related challenges for at least 80 years. You might ask, what new developments underlie possibly making progress now? People report new data about dark matter effects. People might be able to use this data to test candidate specifications for dark matter. Regarding my work, the following sequence pertains. I developed the work far enough to suggest progress regarding the four challenges. Then I learned of data, some previous and some just announced, about dark matter effects. The modeling explains the data, and the modeling offers explanations for other data. This chart points to some of the new data. People infer ratios of dark matter effects to ordinary matter effects. 5 of the first 6 rows show, for galaxies, observed inferred ratios of amounts of dark matter to amounts of ordinary matter. The 7th and 8th rows show inferred ratios for aspects bigger than individual galaxies. The last row shows a ratio, 1:1, for which some people conjecture that the non-ordinary matter effect associates with dark matter. Each row shows an approximate ratio of small integers. I know of no other seemingly significant reported ratios. This data provides bases for testing models of dark matter. This chart points to some aspects of my work. Bases include not only the known elementary particles and concordance cosmology, but also modeling based on Diophantine equations and on an assumption about the number of isomers, or copies, of some elementary particles. I make suggestions and provide explanations that span topics in elementary particles, astrophysics, cosmology, and general physics. Let me provide a glimpse into the modeling that has bases in one Diophantine equation. The equation features sums of integers. Each element of the sum is the product of a small integer, 1, 2, 3, 4, 6, or 8, and one choice of -1, 0, and +1. The notion of a solution associates with a matched pair of sign-reversed expressions. For a solution, if each of the two expressions contains exactly one non-zero element, the word monopole pertains. If each expression contains exactly two non-zero elements, the word dipole pertains. if each expression contains exactly 3 non-zero elements, the word quadrupole pertains, and so forth. Solutions for which sigma is positive associate with a decomposition of electromagnetic fields, a decomposition of gravitational fields, and lists of properties such as charge, magnetic moment, mass, and moments of inertia of objects. Solutions for which sigma is 0 associate with elementary particles, except for the photon, would-be graviton, and 2 other possible elementary particles that would be related to the photon and graviton. Let me finish the glimpse into details of my modeling by suggesting the following regarding electromagnetism. The so-called 1G1 solution associates mathematically with a notion of monopole and physically with both charge and a spatially monopole contribution to the electric field. The so-called 1G12 solution associates mathematically with a notion of dipole and physically with spatially dipole contributions to the magnetic field. The so-called 1G1468 solution associates not with charge or dipole moment, but with hyperfine state for example, hydrogen atoms. Let's discuss elementary particles. Solutions for which sigma equals 0 might associate with all elementary particles other than the photon and possible higher spin relatives of the photon. This slide reprises familiar displays that allude to all known elementary particles. Here I show the spin s in units of h-bar. The slide points to 6 quarks, 6 leptons, 11 spin 1 bosons, including 8 gluons in the photon, and 1 Higgs boson. My modeling points to 5 possible sets of new elementary particles. The 3 spin 1/2 r particles, or so-called arcs, would be zero charge analogs to quarks. The spin 1 j particle, or j boson, would provide for Pauli repulsion. The spin 0 I particle, or I boson, would be the so-called inflaton that people think played a role during the first second after the Big Bang. The letter L abbreviates the phrase long-range interaction. The photon associates with the spin 1 long-range interaction. The spin 2 L particle would be the so-called graviton that people think might associate with gravity. My work points to possibilities for, but does not necessarily require, a spin 3 relative of the photon and graviton, and for a spin 4 relative. The 3 spin 1/2 m particles would be so-called heavy neutrinos. My work seems not to point to some elementary particles that people have looked for and, at least as yet, have not found. Examples include axions, magnetic monopoles, and supersymmetric partners. Let's discuss dark matter. People report ratios of dark matter effects to ordinary matter effects. Possibly, many people do not yet consider that the ratios might have bases in something, quote, fundamental. This chart shows ratios of dark matter to ordinary matter that people report. For some ratios, there might not be very many reports, but perhaps even those results point to what might someday become seemingly prevalent approximate ratios. Hadron-like particles made of arcs and gluons might associate with people's notions of dark matter. Heavy neutrinos might associate with people's notions of dark matter. Each of these candidates for dark matter associates with zero charge and would not interact electromagnetically. However, it seems unlikely that these particles alone would suffice to explain inferred ratios of dark matter to ordinary matter. My modeling points to bases for these ratios. My work posits that nature includes 6 so-called isomers of the set of all elementary particles except LRI, or long-range interaction elementary bosons. I associate with each one of the 6 isomers, the stuff made from that isomer's elementary particles. The stuff associating with one isomer includes ordinary matter. I use the term isomer 0 to name this isomer. Isomer 0 includes some arc plus gluon hadron-like particles, or some heavy neutrinos. Stuff made from isomer 0 arc plus gluon hadron-like particles, or heavy neutrinos, measures as dark matter. All of the stuff associating with the 5 additional isomers measures as dark matter. An isomer does not have its own copy of LRI elementary bosons. To a first approximation, one might say that the stuff associating with each isomer includes the isomer's own instance of photons. A technical statement includes the notion that each isomer associates with its own instance of the solution 1G1, and that each instance of 1G1 has a reach of one isomer. To a first approximation, one might say that gravity connects all 6 isomers. A technical statement includes the notions that there is one instance of the solution 2G2 and that the instance has a reach of 6 isomers. Even-numbered isomers associate with the notion of left-handedness, and odd-numbered isomers associate with right-handedness. Notions regarding handedness might help explain aspects of baryon asymmetry, or the imbalance regarding ordinary matter between observed matter and observed antimatter. Associations between charged lepton flavor and charged lepton mass vary by isomer. Notice, for example, the position of the E, or electron, for isomer 0. For isomer 0, the lowest mass charged lepton associates with what I call flavor 1. For isomer 1, the lowest mass charged lepton associates with flavor 3. For isomer 2, the lowest mass charged lepton associates with flavor 2. Stuff associating with 4 isomers, isomers 1, 2, 4, and 5, evolves quickly into cold dark matter. Isomer 3 stuff evolves similarly to the stuff associating with isomer 0, which is the isomer that includes ordinary matter. The notion that isomers 1, 2, 4, and 5 evolve quickly into cold dark matter helps explain observations regarding the bullet cluster collision of 2 galaxy clusters. Let's discuss dark energy. People report data about the rate at which large objects move away from each other. People tend to talk about 3 eras: inflation, which would occur shortly after a so-called Big Bang; a multi-billion years era in which objects continue to separate from each other, but during which the rate of separation slows; and a recent multi-billion years era in which the rate increases. This chart depicts the notion that gravity mediates monopole interactions, dipole interactions, and so forth. This decomposition of gravity has parallels to decompositions of electromagnetism, in which people associate an electric field with a monopole property, charge, and associate a magnetic field with a dipole property, magnetic moment. In this chart, the symbol 2L associates with gravity. The symbol 1J associates with the J, or Pauli repulsion, boson. The monopole component, quadrupole component, and 16-pole components of gravity associate with gravitational attraction between objects. The dipole component and the octupole components of gravity associate with gravitational repulsion between objects. For each one of the monopole component of gravity and the 16-pole components of gravity, there is one instance. The reach of each instance is 6 isomers. For the dipole component of gravity, there are 3 instances. The reach of each instance is 2 isomers. For each one of the quadrupole component of gravity and the octupole components of gravity, there is 6 instances. The reach of each instance is 1 isomer. Popular modeling seems to underestimate recent growth in the rate of expansion. My work indicates that if people base models for the current era on models for dark energy that fit the previous era, the models will underestimate, for the current era, the expansionary pressure by a factor of up to 2. This chart shows aspects regarding 5 possible eras in the history of the universe. The term RDF abbreviates the forward phrase radial dependence of force and associates with modeling based on Newtonian physics models. The first era would feature the compacting of some form of energy. The driving force would associate with the 16-pole components of gravity, which associate with attraction and with reaches of 6 isomers. Presumably, some elementary fermions would form. A bounce, based on Pauli repulsion effects that would associate with the J boson, would associate with notions of a Big Bang. Instances of the J boson, or Pauli repulsion boson, have reaches of 1 isomer. The isomers would already be evolving somewhat independently of each other. Concordance cosmology and my work point to the third era. People use the 2-word term inflationary epoch to name this era. The inflaton elementary particle would play a key role. Octupole components, which would be repulsive, of gravity provide for rapid flying away from each other of objects. People have data about the 2 most recent eras. My work points to the notion that the quadrupole component of gravity triggers decreases in the rate of expansion that characterize the next to most recent era. For the inflationary era and the next to most recent era, key instances of components of gravity have reaches of 1 isomer. The driving force for the current era is the dipole component of gravity. Each one of the 3 instances of that component, which is repulsive, has a reach of 2 isomers. Other people's models underestimate recent increases in the rate of expansion because of the difference between the reach of 2 isomers and previously applicable reaches of 1 isomer. Regarding modeling based on general relativity, possibly people can adjust assumed equations of state to reflect larger than currently assumed dark energy pressures. Let's discuss galaxy formation and evolution. This slide shows evolution on the scale of 1 galaxy regarding attraction and repulsion of stuff. A key point is that many early galactic halos might tend to feature just 1 isomer. Among such galaxies, as many as 5-6 might be dark matter galaxies, and the remainder might feature much ordinary matter. Some of these galaxies survive, relatively untouched, until now. These phenomena explain ratios of dark matter to ordinary matter of 1 to approximately 0 and of approximately 0 to 1. Other such galaxies repel 1 isomer of stuff and collect 5 isomers of stuff. These phenomena explain ratios of dark matter to ordinary matter of approximately 4 to 1. Captures of 1 galaxy by another galaxy lead to galaxies with dark matter to ordinary matter ratios of approximately 5+ to 1. The discussion about galaxy evolution suffices to explain most of the observed ratios of dark matter effects to ordinary matter effects. I now address other ratios. Regarding larger entities, such as galaxy clusters, I assume that ratios related to densities of the universe pertain. Regarding some depletion of CMB, or cosmic microwave background radiation, people suggest that half of the depletion associates with hyperfine interactions with ordinary matter hydrogen atoms. My work indicates that the other half of the observed depletion associates with hyperfine interactions that involve isomer 3 hydrogen-like atoms. I show this chart mainly to indicate that my specification for dark matter might comport with observations regarding the bullet cluster collision of 2 galaxy clusters. If my work did not point to differences between isomers regarding matches between lepton flavors and lepton masses, my work might not comport with inferences that most dark matter does not engage much in electromagnetic self-interactions. Let's discuss some possible links between physics constants, properties of objects, and aspects of fields. Across all elementary bosons, the squares of masses relate to the square of one mass and to integers, some of which associate with spin and charge. The ratio 7:9 of the squares of the masses of the W boson and the Z boson associates with the weak mixing angle. The tau elementary particle and the electron are two of three charged lepton elementary particles. I suggest a relationship between the ratio of the tau mass to the electron mass and the ratio for two electrons of electrostatic repulsion to gravitational attraction. This relationship interrelates some properties of elementary particles with some aspects of electromagnetism and gravity. This set of formulas computes a tau mass for which several standard deviations fit within one observed standard deviation. I suggest a formula that interrelates the masses of the 9 known charged elementary fermions, each one of alpha, the fine structure constant, and beta prime, the ratio of the tau mass to the electron mass, appears in the formula. The formula comports with measured masses. The left side of this chart shows logarithms base 10 of ratios of elementary particle mass to electron mass. The integer variable L sub m associates with fermion flavor. The integer variable L sub q associates with 3 times the magnitude of the charge in units of the magnitude of the charge of the electron. The notion that the charged lepton flavors do not align, with respect to the formula, with quark flavors points toward differences among the 6 isomers of elementary fermions. The right side of this chart shows, in parentheses, 4 numbers that the formula produces but that do not associate with known or predicted elementary particles. For each column, the numeric spacings between numbers are orderly but not exactly uniform. Applications of the formula that interrelates the masses of the 9 known charged elementary fermions estimate the masses of the 3 known neutrinos and the masses of other possible elementary particles to which my work points. Regarding the known neutrinos, the notion that at least 2 neutrinos associate with the mass to which the chart alludes comports with limits on the sum of neutrino rest energies that people infer from astrophysics data. This chart shows rest energies that people report or my work indicates. My work points to a result and small standard deviation for the tau rest energy, to the notion that at least 2 and perhaps all 3 neutrinos have rest energies of about 0.034 electron volts, and to the notion that rest energies for the would-be arcs would be similar to rest energies for some of the quarks that associate with the 2 lower mass flavors of quarks. The chart shows one lower limit for the rest energies of the would-be heavy neutrinos. Another possible lower limit would be more than 1 billion GeV. How might people test, use, or extend work that I've discussed? People might develop detailed modeling and simulations regarding large-scale physics, galaxies, galaxy clusters, and so forth. People might try to observe large-scale phenomena and detect small-scale phenomena. Also, opportunities exist to continue to unify and deepen modeling within my work and between my work and other work. This presentation suggested advances regarding various physics challenges. Compared to other attempts to address the challenges, the following notions pertain. My work seems to feature more reuse of extant concepts and modeling. My modeling seems to feature simpler mathematics. my work seems to explain otherwise unexplained data. This presentation discussed highlights of my work. For further details and information, please feel free to look at online information or to contact me. Thank you for your interest in new thoughts, suggestions, and results about the mysterious world of elementary particles, dark matter, and dark energy.